So, by virtue of the fact that sine waves and cosine waves are periodic signals, when you add up periodic signals, intuitively you're going to get periodic signal also, right? That's my intuition, right? To understand the cost material, you need a lot of intuition. Okay? But is it true that all signals that are given to you for analysis are periodic? Obviously not true, obviously not true, obviously not true. I don't speak like that, right? I don't speak periodically, right? So every sentence that I give it to you for frequency analysis is obviously not periodic, right? So how are we going to extend our analysis on periodic signals, which is Fourier analysis, to non-periodic signals? And this is a technique that we will do this morning, and it's called Fourier transform. Okay, and just do a thought experiment. So if you have a periodic signal, right, whatever signal you have, and then it repeats itself, right? That's periodic, right? And the period is this, right? Yes, right. Now, if you are given a non-periodic signal, right, what Fourier transform does is we will still want to treat it as periodic. It's just that the period is infinity, you understand? It stretches from minus infinity to plus infinity, right? And then it will repeat again as infinity, but infinity is something that is hard to imagine, right? So let's just take it that the signal is periodic. It's just that it's from the t is from minus infinity to plus infinity. So the fundamental period is infinity, you understand? Yeah? Okay? And with that extension, we can now apply our usual Fourier analysis. Okay? Fourier analysis to get the frequency that we are looking for. Okay? That we are analyzing, the signal that we're analyzing to get the frequency component. And so this is known as Fourier transform. Okay? And Fourier transform is a very, 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 very useful tool. I can't imagine if there's anything in our real life here that can be done without any Fourier transform. I mean, there are many, many things. Even a cell phone or whatever, there are certain things, certain components in there that has to make use of this concept. Okay? So we have a non-periodic signal, right? This signal is obviously not periodic. This signal is a typical shape that you see for speech signal, right? The speech signal looks like that, right? The speech signal looks like that. In fact, this speech signal is a speech signal for may the force be with you. Does it sound familiar to you? You're too young to know that, right? May the force be with you. It's a sentence spoken by Yoda in Star Wars, right? May the force be with you, and it looks like that. Okay. So the axis, the axis is time axis, right? And then the y-axis is the amplitude of the vibration in the air. Understand? The amplitude of the vibration in the air. Okay. So if you use later part of the tutorial, some subsequent tutorials, right, you'll be able to know how to discretize your own voice, record your own voice, right? If you record your own voice and then you look at it, it looks something like that. I think you see this kind of thing in movies also, right? Right, so this is typical of a human spoken signal, right? So this is may the force be with you. To complete this course also successfully. So it is not periodic, and we are going to treat this as periodic, and we're just bluffing ourselves to say that the period is infinity. Okay? from myself. That so far is known as Fourier series, right? In our previous lecture. Just to recap again, just recap. You know, when we deal with a signal like that, it is a vector of many thousand elements, right? Yeah? A long vector of many thousand elements, correct? Okay? But when I ask for intuition, you have to think of intuition at a lower dimension, right? Because what happens in the lower dimension applies to higher dimension also, right? So in the lower dimension, you think of three dimensions, okay? So if you have x, y, and z axis, right? You can represent all points in the 3D space, right? And every point will have a coordinate x, y, z, right? So every point will coordinate x, y, z. And what is the coordinate of x here? This is 1, 0, 0, right? This is 0, 0, 1. No, sorry, 0, 1, 0. And this is 0, 0, 1, right? Yeah? Right? But to represent all the points in this axis, you want the three axes to cover the 3D space. And you want them to be orthogonal to each other, right? It's easier. We went through this last semester, right? Last lecture, right? Right? But can this be a good representation of the points? Of course it can. As long as they cover three-dimensional space, they are 90 degrees to each other. This is equally good, understand? This axis is equally good, okay? Right? But what's the coordinate now? It's no longer so nice 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? Right? It's no longer so nice. It will be some numbers. Some will be negative number, positive number. Some messy numbers, right? Yes? Yes? But it's still good as an axis, okay? Okay? So imagine instead of three-dimensional space, you have, say, 1,000 dimensions. 1,000 dimensions. So you have 1,000 of these orthogonal to each other. Now we cannot imagine now, right? Right? But you know that if you take the vectors, you dot product with each other, it will give you 0. Understand? Okay? So in the 1,000 dimensional space, you will be able to rotate all the set of orthogonal vectors in such a way that the numbers now, if you plot them on a curve, right? The numbers now, some will be big and then small, positive, negative, and then you can rotate them in such a way that all of them represent sine waves and cosine waves. Understand? Yeah? And why we can do that? Because last lecture we also know that sine and cosine are orthogonal to each other, right? Right? So there's reason for us to believe that you can achieve that, correct? Okay? So you rotate the vectors in such a way that every one represents sine waves and cosine waves of different frequencies, understand? And they are all orthogonal to each other, right? We did it just last week, right? Right? So we do that, and then And then we say that the point in the 1000 dimensional space can be represented as the summation of all the 1000 basis vectors, right? Which are all sine waves and cosine waves, right? Yeah? And then we also know just now that that when you add up periodic signals together, you are going to get periodic signals, right? Intuition, right? And then we say that let's start with the periodic signal first, right? And then we analyze periodic signals last week, right? And then we successfully can know that it is indeed the case, right? I'm going to give out the next tutorial later today, right? You'll be doing, you'll be applying the Fourier analysis work, okay? So we can think of, so now we want to extend it to non-periodic signals, and we want to think of non-periodic signal as a periodic signal with period equal to infinity, right? Then we apply the same tools to analyze such periodic signal, and we call this generally Fourier transform. Okay? Now, pray very hard then you advance by one slide. So in other words, for periodic signal, we can still do Fourier series analysis by assuming that the signal is periodic with period equal to infinity, right? So remember, recall that when we do the periodic signal, we only do sum, multiply and sum for one period, right? Yes? Right? Can you do for 2 periods and 3 periods? Can you do that? Who say yes? Who say no? Who don't know what I'm talking? No response. By the way, the school just implemented some lecture attendance kind of QR code. I will flash it later. So the answer is you can. Okay, as long as it's complete period, you can do 2 periods, 3 periods, it's fine, right? But it's still limited time, right? But now we are talking about the period being infinity, and therefore we cannot just sum them over a finite period, understand? We have to sum them over infinity, right? Which is what, the top one is periodic signal, right? You sum them over a complete period. You can sum to 2t can also, 3t can, doesn't matter. Why doesn't matter? If you sum a period like that and then it repeats itself, you sum again, right? The integral here compared to this integral is how many times? 2 times, understand? But it is the same factor that applies to everybody, every present component, so it doesn't matter, understand? It doesn't matter, understand? Because loudness doesn't matter, understand? Loudness doesn't matter, it's the frequency, relative frequency content that defines what you see. Okay? So, you can actually safely integrate to 2t or 3t, it doesn't matter, as long as it's integral. But then for the non-periodic case, you better integrate from minus infinity to plus infinity, right? Because that's the whole period, that's one period. Okay? So from there, you easily transform, move you to, you can actually transit from there from Fourier series into Fourier transform. Any question? It's just like that, the concept is still the same, understand? So when we do Fourier transform this forward, right? That's from time domain signal, my speech. The time domain signal may the force be revealed at that background, right? The vibration in the end, the time domain signal. When you do Fourier analysis, it goes to frequency axis, right? Frequency domain. So the axis now is how many hertz, right? 0 hertz, 0.1 hertz, 0.2 hertz, etc., right? Yes? Right? So when the horizontal axis is time domain, is time axis, you call it time domain signal. When the horizontal axis is frequency, you call it frequency domain. Understand? They are equivalent. They are equivalent of the same physical phenomenon. Understand? Which means that I can represent a signal using that, or I can represent the signal by the frequency component. Understand? They are the same, okay? So when you do a Fourier transform or Fourier analysis, you bring from time domain signal to frequency domain, right? So naturally, you can actually go back to representing it using time domain, right? And that process is called inverse Fourier transform. Right, you bring the frequency domain representation of signal back to its time domain representation. Okay? So you have Fourier transform, you have inverse Fourier transform. Inverse Fourier transform is extremely, it looks similar to Fourier transform, right? So what's the difference? Answer is there. Just tell me what's the difference. Just too quiet. What's the difference? Someone. Come on.
The exponent is positive.
Sorry?
The exponent is positive.
The exponent is positive for inverse Fourier transform. Very good. Right? And what are the other differences? The exponent is positive for inverse in compared to, right? And then somebody say you integrate what?
You integrate with respect to either the radian frequency or the...
Yeah, you integrate with respect to time or with respect to frequency. Okay? Right? And the third one is of course what you want to operate on, right? The time domain signal becomes a frequency domain. A frequency domain signal becomes time domain, right? Okay? Okay? And there is a 1 over 2 pi here, right, to make the mathematics correct. Meaning if you just substitute this thing in here, you get xt with xt, you understand? Okay? But for this course, I go to maths department, maths professors will shoot me, understand? Because I'm not very exact. I'm shooting for the real, I'm shooting for intuition. So for understanding the materials in this course, I'll just say again, loudness does not matter, understand? So the factors in front, not important to me. Okay? The factors in front, not important to me. Alright? So when you do the trapezoidal rule for integration, I'll just ask you to add up. I don't ask you to multiply by the height of the trapezoid. Right? Understand? Because strictly speaking, you need to multiply by the height of the straight, right? The width of the straight, right? Because the loudness does not matter. Understand? Okay? That's why I keep on saying area under the curve is just dot product. Strictly speaking, you need to multiply by the gap, right? Of the trapezium. But let's not worry about that because loudness does not matter. Okay? Any questions? Now, there are a few very important things that we have to go through this time. In fact, I realize some of the practicing engineers outside actually don't realize this. Okay, so you have to pay attention. You have to pay attention. There are a lot of things that will happen because you see, we talk about time domain signal, right? Continuous time axis, right? You see the continuous time axis. But the moment when we use computers to compute the signal, we end up having to discretize the time axis, right? And when the moment you do discretization, it has a profound effect on the entire understanding, understand? Okay? It has got a lot of non-intuitive effects. Okay? So you have to realize this. The effect of discretization on time or frequency axis. Okay? So I'm going to use this notation. Every time you see a curly bracket, it means continuous, understand? So small t is continuous, right? Every time I use a square bracket, it means discrete. Okay? So n is integer now. Okay? N is integer now. And t is a time in seconds. So discrete time simply means the time axis is discrete. N represent integers. The discrete time function can have continuous values. Understand? This is also one thing that a lot of people get confused. Okay? And only n is integer, but x of n can be 1.2, 1.3, 3, understand? Okay? Or 1 point whatever. Right? So this is a continuous function, and then in discrete time, you just sample them, right? You sample them at fixed intervals, right? And then you represent this continuous curve by an array in your computer, right? So that's discrete time. Okay, so from now onwards, you look at discrete time x over n. Now, so let's see the next few slides will bring us from continuous to discrete, and then we see what happens. Okay? Now, when you discretize into an axis, let's say at the position, let's say if you have 5 units on the vector, right? What does it represent, the time interval? What does it represent? It represents 5 times the delta t, right? The sampling interval, right? Yes? Yes? Yes or no? Yes, huh? So, and then we use capital N to represent the length of the vector. Capital N is the length of the vector, right? So delta t is equal to the entire period divided by n, right? Entire period divided by n, right? Okay? Okay? Now, if you look at the continuous Fourier transform equation, by the way, omega is equal to 2 pi f. You all know, right? From physics, you know, right? Right? Because f is how many rounds per second. Omega is how many radians per second. 1 round is 2 pi, right? 2 pi radians, so it's 2 pi. So omega is 2 pi f. So we sometimes use f, sometimes use omega interchangeably. Okay? And from here to here, no problem, right? From here to here, right? From here to here, this is how we write our Fourier transform in the discrete time domain, right? This is how we write Fourier transform in the continuous time domain, right? We want to check the relationship between this and this, understand? Okay? So from here to here, you know that delta t is equal to n times t divided by n, right? Right? Okay, nt divided by n. So delta t, you replace it by this. Okay? Okay? And then since you need to multiply by delta t here, you put it here. Can you see that? You're changing from the continuous time integration into discrete time, right? Continuous time integration into discrete time, right? So you multiply by delta t here, right? You multiply by delta t here. Okay? Okay? Yes?
In the first slide, what is n full stop delta t plus full stop?
N times.
Oh.
This means times, full stop is times, multiply. No problem, right? From here to here, no problem, right? Yeah? And then, since delta t is equal to t over n, you write it this way. I write it this way, okay? Okay? Now, I just copy this one to the next slide, and you get this, right? You get this. Okay? Now, I discretize the time axis, and you get this equation on the top here, right? Right? Okay? Now, when we do the Fourier analysis, you also represent the frequency axis in the frequency domain using array, right? Yeah? So your frequency also get discretized, right? Yes? So I'm going to say for just now delta t is the sampling interval is delta t, right? In time domain. In frequency domain, I'm going to say k naught is my frequency step. Understand? K naught. Understand? So therefore, the frequency f naught is my frequency step. Sorry, f naught. F naught is a frequency step, right? And f naught is equal to 2 pi f naught is equal to omega naught, right? Right? So omega naught or f naught is my frequency step in my frequency axis in the frequency domain, right? Okay? So for every location in the frequency domain, it represents an increment of k naught. Oh, sorry, f naught. Increment of f naught, understand? Okay? Is that alright? So you have this, and then k becomes like the n in the time axis, understand? The index. Right? The small k is the index of the array in the frequency domain. The small n is the index of the array in the time domain, right? Okay? Okay? So you can write it this way, and f naught is equal to 1 over t, right? Right? F naught is the, we define it that way. We define it that way, right? The t is the period of the signal, right? T is the period of the signal, okay? And then 1 over t is the f naught, is the frequency gap, okay? Okay, so in the frequency domain, every gap, right? The gap is determined by the period of the signal. Okay, and this is very important. This is very important, right? And if you do some manipulation, you bring all this, you instead of saying x of omega, you go to the discrete frequency domain, and then discrete frequency axis, and then you index it by k, right? Right? Every omega is represented by k times omega naught, and omega naught is given by 2 pi 1 over t. Okay? And then you just plug it in. Omega is 2 pi 1 over t and t over n, and then you do some simplification, you end up with this expression. Okay? Okay? And that's the Fourier transform equation, right? Never mind this factor here, t over n, never mind, because it's just a scale factor, understand? Right? If you look at the summation itself, it's Fourier transform, right? I have a bad feeling that you're not following or you're finding bored, because by looking at the face, I get that feeling. How many of you say I'm too slow? How many of you say I'm too fast? How many of you say you don't understand what I'm talking? You have to let me know, huh? You don't understand? Yeah. Sorry? Small n is the, you have the time axis t, right? That's continuous, right? Right? And then you discretize by sampling the time, right? So time 0, time 1 millisecond, 2 millisecond, 3 millisecond, 4 millisecond, right? And then you put them into an array, right? Small n is the index of the array. That means when n equal to 5, it represents 5 milliseconds. Understand? Big N is total number, the size of the array. Big N is the size of the array. That is the total number of points. Okay? Big N is the size of the array, the total number of points within the period. And small n is the index, the position of the time within that array. How do you find the period t? Is it period t for the time being? Let's not worry about what is the t. Let's think of a generic generic periodic signal first. That is called the period T. Understand? Whether P is finite, infinite, doesn't matter. But that is a T, the period. Understand? Any other question? So, so you end up with the equation that you're familiar with, and that is the equation for Fourier transform, right? Right? Now, so I just copy the equation again, right? And see, I wrote the T over M here, but it's not important, like model doesn't matter. Just focus on this part. Okay, just focus on this part. Okay? Now, the strange thing when you do the discretization is you end up having to deal with periodic signals, understand? Okay? Your signal is not periodic, but the moment you go and discretize the axis, you find that the frequency domain becomes periodic because x of k plus capital N, right, becomes x of k again, understand? I give you like 30 seconds to read through this. This is not difficult, right? Right? E to the minus j2 pi n is equal to, what is e to the power of e to the power of minus j2 pi n? Who can tell me what is it? Minus j2 pi n. N is an integer. E to the minus j2 pi n is equal to cosine 2 pi n minus j sine 2 pi n, right? This is the Euler's rule that we saw last week, right? Yes? And what is cosine 2 pi n when n is an integer? 1, huh? And what is sine 2 pi n when n is an integer? 0. So e to the minus j2 pi n is equal to 1, understand? So for that reason, this term can be taken out because e to the minus j2 pi n multiplied by this is, in case you forgot your exponential thing, minus j2 pi 2 pi k n over n, k n over n e to the minus j2 pi n is equal to, minus j2 pi n. The two exponents like that is equivalent to this, right? It is equivalent to this, isn't it? Yes? And this is 1, so it can be taken out. Okay, so from here you can get to here, right? Right? Which is exactly, you go back and then go back to the same item. So k, if you take one period away, is the same as a k, right? 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 So, and this is what I say a lot of practicing engineers didn't know about this actually. Sorry, I was talking about, I didn't switch. Right? So so x of k, you add the period and then it becomes x of k again. Okay, so it's periodic signal, understand? And that was what I meant when I say a lot of practicing engineers don't know about this, right? So you have to be careful. Okay, sorry? Today is a bit funny, right? Can you just look at this side? Right? So x of k is periodic with period n. So what does it mean? What does it mean? What does it mean? It's like, what it means is this. If you have an axis here, right? You go and discretize your time axis, right? You discretize your time axis. Okay? In the frequency domain, the signal becomes periodic, you know. Like this is not intuitive at all, right? It is because of the mathematics we use, right? frequency domain to time domain is inverse Fourier transform, right? The mathematics, are they similar? They're almost the same except that the power is minus, one is plus, one is minus, right? Right? So there's something called a duality, right? What happens in this way also happens this way, understand? So in the frequency axis, you also represent the frequency by discretizing the axis, right? Yes? Okay? So in the frequency axis, the index of the frequency axis array is small k. Small k, right? Yeah? Okay? And the length of the axis is also capital N, right? We take it as capital N. So the same thing happens because we are using computers, right? We represent the frequency axis using discrete intervals, right? Using an array. And therefore, what happened to the time axis? What happened to the time axis? What happened to the time axis? In the time axis, when you discretize the axis, frequency domain, we just see that it is periodic, right? You have to be periodic, and math indicates it that way. It's non-intuitive, but the math dictates it that way, right? Now when you discretize your frequency axis, what should the time axis become? Become what? Periodic, very good, periodic. Okay? So in other words, listen, in other words, when you do discrete Fourier transform, here we're talking about discrete Fourier transform, right? Right? We're talking about this both axes in time and frequency domain discrete, right? Right? When you are playing with discrete Fourier transform, and you will always be doing discrete Fourier transform because that's what the computer can do. The computer cannot handle continuous time, right? Right? You are always dealing with periodic signal, understand? So in other words, if I send this sentence to your Fourier transform, discrete Fourier transform analysis, if I send this sentence for your Fourier transform, right? Your discrete Fourier transform. Okay? The mathematics will assume that my signal is this, if I send this sentence for Fourier transform, if I send this Fourier sentence for Fourier transform, my mathematics will assume I speak that way, understand? Understand? A very crucial part, the mathematics will assume that way. So when you do discrete Fourier transform, you have to be careful, understand? The mathematics is going to assume that if I send this sentence to Fourier transform 0 outside, it's not like that, understand? It's going to assume that it repeats itself. Is that clear to everybody? Okay? So number one lesson to learn from periodic signals to non-periodic signals, we know that we can extend the period to infinity, right? To treat it as periodic signal, and then we get Fourier transform, continuous Fourier transform, continuous time Fourier transform, right? Right? But the moment you represent it using computer, discretize the axis, the other domain becomes periodic. Okay? Okay? Because the mathematics dictate it that way. Right? So similarly, Xn is also periodic with period n, right? It's non-intuitive, but because you're using discrete Fourier transform, that is the case, understand? Okay? So you have the Fourier transform here. Forward Fourier transform, right, from time domain to frequency domain, inverse Fourier transform from frequency domain to time domain. Right? So you have different types of Fourier transform now, understand? Different types of Fourier transform. Right? The one that we say, we assume the period is infinity, right? It's called continuous time Fourier transform. The first equation here, understand? Okay? Continuous continuous time Fourier transform. The time is continuous. The frequency is also continuous, understand? Okay? Now, so that's continuous time Fourier transform. There is a second type of Fourier transform which you don't use also, but it exists, understand? It exists. Sometimes you do want to consider it in this way, sorry. It's not that we don't use it. It's just that you will compute it in your computer, but conceptually you have to use it, understand? The second type is called discrete time Fourier transform. And discrete time Fourier transform is for the case when your time axis is discretized. Your time axis is no longer t. Your time axis is small n, understand? But the frequency axis is still a continuous variable omega, understand? Yeah? You only do discrete time only. And discrete time Fourier transform, what will be the frequency axis? You discretize the time axis, your frequency axis is periodic, understand? So discrete time Fourier transform, your frequency, your spectrum is periodic, understand? Yes? Okay, and then the third time is a discrete Fourier transform. Discrete Fourier transform is, let's go to the frequency axis and discretize it also. When you discretize it, the other side, the time domain also periodic, right? Right? So this is the case when everything is discretized. The time axis and the frequency domain axis both are discretized, and because of that, both sides must be periodic, understand? Okay? And discrete Fourier transform is what you will be using most of the time. Discrete Fourier transform is what is out there in all the appliances that they use it all the time. Okay? Right? There's a fast implementation of discrete Fourier transform called FFT, fast Fourier transform, understand? So when you see 5FT, when you see FFT, it's equivalent to DFT, understand? It's just a fast implementation. And so when you see FFT, what must be periodic? The time and the frequency, understand? Okay, so if you send in your signal like that and send it to FFT, don't think that outside is zero, understand? The math would assume that this repeats itself. Okay? A very critical point, huh? Any questions so far? Do you understand what I'm saying? If you understand, can you just nod? Oh dear. Yes.
How do you relate K to the actual frequency?
K relates to the actual frequency, K times F naught.
Okay.
Right? F naught is the gap in the frequency domain. Who don't understand what I'm talking? You have to give me your feedback, otherwise I don't know how to continue. Huh? Once again, do you understand what I'm talking now, this morning? You don't understand? You understand? Some understand, some don't understand, some just no response. So, I'm not going to remember who understand, who don't understand. I just want to get a sense of whether the explanation is clear or not. If not, I'll repeat. And then if you understand, you don't tell me you understand, I'll repeat and then you get lost. Right? So, who wants me to repeat? Okay, can you tell me which part you don't understand?
The very important key point you mentioned.
Okay, the key point I mentioned is, okay, if you have time domain axis t, right? This is continuous time, right? Right? And then you represent it in the using arrays. Becomes n, right? And from here to here is a delta t, right? Right? And then let's say if this is 5, let's say if there are 5 units here, right? So the time here is equal to n times n is equal to 5, right? So 5 times delta t, understand? So that's a discrete time. That's what I meant by discretize the time axis. Okay? Now when you do time axis and then you do Fourier transform here. Continuous time Fourier transform, right? Continuous time Fourier transform, you've got the frequency axis or the omega axis here, right? Right? Yeah? And then you get some kind of spectrum. Okay, you get some kind of spectrum. Okay? With zero outside. Understand? Okay? How you get this is by Fourier transform, alright? I'm just drawing arbitrary pattern here. Now when you discretize the time axis, you get a discrete time Fourier transform, understand? It's discrete time, right? So when you have discrete time Fourier transform, you expect to see this in your time domain, your frequency domain, understand? It repeats forever. It repeats forever. Okay? Okay? Now, if you also discretize this axis by k, right? So k. So if there are 5 units here, right? You represent the frequency is equal to 5 times delta f, right? And the delta f, we call it f naught, okay? 5 units of frequency. 5 units of fundamental frequencies, understand? Okay? And because you discretize the axis here, let's say if this is your, may the force be with you, right? Like that, right? The time domain signal, they will assume that you have some signal here, right? Sorry, you have some, may the time be with you, right? You assume that outside here, even though it's not represented by your array, right? Outside here is all, may the force be with you, understand? Understand? Okay? May the force be with you, may the force be with you. Is that clear now? So, there were 2 other hands that put up, what was your question? Okay now. I appreciate you asked the question in class, right? It's okay to share your question, because usually there are common questions, and you ask, somebody will get a better understanding, okay? Okay? Now, inverse Fourier transform, same thing. You have you have the inverse continuous time Fourier transform, inverse discrete time Fourier transform, inverse discrete Fourier transform, IMFT, same thing. Okay? So I wouldn't yeah. So this is an illustration of what? Nobody. Okay. So this is an illustration of what? Now it's okay. This is an illustration of what? This is an illustration of what I just mentioned, right? When you have the continuous time signal, right? You get the, and if you have a continuous frequency axis here, you get a so-called spectrum here. Okay, the frequency component here, frequency. And when you discretize it, this frequency becomes periodic. Okay, and it replicates forever, that's the right side. Right, and if you also discretize this axis, this signal becomes periodic in time domain, understand? Okay? But in your array itself, of course, you only represent one period. Right? Mathematically outside is still the same. Outside repeats. Yes, Simon.
When does the frequency domain repeat? What is the boundary?
The boundary is it depends on how you sampling them. How you sample them. So it could be like that, it could be longer, things like that. Right? The boundary has got to do with the sampling frequency and how you sample it. So we'll do it next time. Okay? But that's a very good question. Okay? Now, so we know there's Fourier transform, and we know repeat again. Last week we analyzed periodic signals using Fourier analysis. And this week we say we don't want to restrict ourselves to just periodic signals. So we do Fourier transform, right? Right? And then we found that because we use computer to discretize the time axis, use computer to discretize the frequency axis, we are back to square one. We have to deal with periodic signal, understand? Understand? So we went one big round, right? One big round. Periodic signal, and then non-periodic signal. And because we go and do computer, right, discretize the time axis and frequency axis, we are back to square one, right? We are back to square one, okay? So actually, FFT is like a Fourier analysis or Fourier series, understand? Okay? We are back to square one, huh? Okay? In fact, FFT is not like Fourier series. In fact, Fourier series is more like discrete time. It's more like Fourier series is more like discrete. Fourier series is more like the time axis is continuous, the frequency axis is discretized. Okay, so it's different. If you don't understand what I'm saying, it's okay. Don't worry, huh? But what I'm trying to say is we start with Fourier analysis, right? And then we know that because we use sine, cosine, it is periodic, and then in order to deal with non-periodic signal, we assume the period is infinity, we go to Fourier transform, all is good here, right? And then we find that because we want to use computers to compute Fourier transform, we have to discretize the time axis and the frequency axis. But when you do that, you go back to the requirement that our signal must be periodic. Okay? Okay? So there are ways to circumvent this problem. We have to use this. We have to use it knowing that it is assuming it's periodic, right? But there are ways to mitigate the problem. But you have to recognize that this problem exists first. Okay, and this is something, let's say again, a lot of people make mistakes, even practicing engineers also make mistakes because they didn't realize it. So it's useful to know a few common Fourier transform results, right? We need to know a few. Actually, there are a lot of, there are something called Fourier transform tables. You can find from our Fourier transform time axis to frequency axis and vice versa, things like that. But I only extract a few that you need to know, right, to understand the rest of the form. So we will need to know the results of Fourier transform of impulse, train or impulses, rectangle function, sine, cosine. We need to know these results obtained for both the discrete time, discrete Fourier transform, and the continuous time Fourier transform, right? And later on, we'll need to take a break now, but later on, we'll understand what is meant by impulse. Okay, we take a break now, we come back at 11. Thank you. Okay, can you all scan this? This one is what the school just implemented for lecture attendance. Can you all scan? Can you all scan this? And mark your attendance. Now when you're doing this, okay, now, there was some questions. Yeah. So like, while I'm still doing the QR code, I'll just say this. In our real life, we don't deal with periodic signals, right? Right? And in the frequency domain, it is not periodic like that also. That means let's say we generate some noise, right? Our human audible range is from how many hertz to how many hertz we can hear? 20 to 20,000, right? 20 to 20,000. And this is probably the kind of voice. Our voice is actually very low frequency, right? Now in the Fourier domain, the frequency component is just like that. It doesn't repeat, understand? The repeat of the repetition, the periodic signal, is a mathematical construct, not in real life, understand? In real life, it doesn't happen. But because we are using discrete Fourier transform FFT, we have to take note that actually the mathematics assume it that way, understand? Understand? Okay? Now I'll give you a preview first how to circumvent this, right? Since we know that this is a problem. What you can do is, right? I'll pad with a number of zero. Understand? So that when it repeats later, right? It repeats later, it is like there's a gap between the two real signals, understand? Right? And that kind of things can give you can let you get away with this periodic signal concept. This periodic signal problem. Okay? If you don't do that, then there will be certain processing that you end up having problem with. Okay? You will get weird results. Okay, so has everyone registered your attendance? Okay, huh? Okay. So it's useful to know a few common Fourier transform results, right? We want to see. So a very important concept about what we are going to do in one or two lectures, for the next one or two lectures, is the concept of impulse function, understand? And impulse is not something that difficult to understand. Impulse, what is impulse? Impulse is, you know, when you go shopping, there's impulsive shopping, right? Right? Because of COVID, you haven't been shopping for a long while, and then when shopping mall opens, you go there, you pack with the 3 or 2 years or how many years of your desire to shop, and then you buy a lot of things one shot, right? That's impulsive, right? So you pack a lot of energy and you deliver it within a short period of time. That's impulse, understand? Impulse. That means I punch you, that's an impulse, right? I push you, that's not impulse because it's very long period of time, right? I punch is like within a short period of punch, that's it, right? Right? So impulse is packed with high energy within a short period of time. Okay? So that's the definition of impulse. Okay? Now in the continuous time, in the continuous time domain, okay, there are some terms that people use. Don't be fooled by those terms. Sometimes you see very complicated sounding words, but they mean very simple things, right? So you have Kronecker delta, you have delta, whatever function. It doesn't matter. I'm not going to be too concerned about the names. Okay, you just need the concept is more important, right? Impulse. Okay, in the continuous time axis, an impulse is you pack with a lot of energy, infinite energy. But the time that it delivers the punch is almost zero, understand? Okay? So almost zero but infinite energy. Okay? And 0 times infinity is equal to 1, understand? No maths professor here, no gun, nothing. I am safe to say this. Okay? Okay, infinity times 0 is equal to 1, right? Okay? So that's the definition for impulse in the continuous time domain. In the discrete time, it's even simpler. It's just a half of unit length 1, understand? Discrete time. So that's impulse, not impulse. And the rest all zeros. That's all zeros. These two dots should be 1 dot. This should be 1 dot. Okay? Now, discrete time impulse function. Okay? Again, I think a lot of students get lost when they look at equations like that. Okay? Now I'm going to tell you, if you are having problem with all these things, bracket n plus n or whatever kind of things, right? Not to worry too much about it. Okay? There are only a few things, a few rules that I want you to remember. Okay? Now, first of all, the notation first. Delta, right? We use delta to represent impulse. Okay? Now, this is a train of impulses. Forget about all the math notation. Forget about it. Okay? Just listen to what I say. This is a train of impulses, and it repeats at n intervals. That means there are a lot of points here, understand? There are a lot of points here that are 0, understand? There are a lot of points here that are 0, and the period is n, capital N, understand? So this impulse is of period n, right? Every period n points away, it gives you an impulse, understand? Okay? And when you have 1 point like that, it's impulse, right? Of unit length 1, right? When you repeat this after n points, you call it the impulse train, understand? Or train of impulses. Okay, it's like a train, right? A train of impulses. Forget about all the math notation. Now, discrete Fourier transform has, right? Now, I may have confused you just now. Forget about what I just said. Forget about what I said about impulse. Just look at one interval like that. You have one impulse, right? So you are going to represent one impulse using your discrete time axis, right? but you know that we have to assume that it repeats every n points, right? Periodic, right? Okay. So in mathematical world, even though your interval is from here to here, 1 impulse, right? The math will assume that your impulses repeat, right? Right? Okay? So this is not the train on impulses. I made a mistake just now. Okay, it's not a train on impulses, it's just one impulse, understand? It's just one impulse, huh? And when you have one impulse, just one impulse, it is represented as 1, 0, 0, 0, right? Capital N is 4 here, understand? Capital N is 4 here, right? So within a period of 4 points, you have 1, 0, 0, 0. So this is an impulse, right? Right? And then mathematically you repeat again, understand? Okay? Okay? Okay, not a train on impulse either. It's one impulse, okay? And when you have one impulse, listen. I'm not sure whether this is intuition, but you have to make it, you have to remember this, huh? When I pack all my energy and I give you a punch, that punch comprises all kinds of frequencies, understand? Think of it this way, Think of it this way. Think of white light. Light is actually electromagnetic wave of different frequencies, right? Different wavelengths, different frequencies, right? When you add up all kinds of frequencies, you get something white, right? You get white, right? Right? And then white is like you punch with everything, you pack everything together, right? Right? Think of it this way. So when you have an impulse, when you do Fourier transform, the answer will be all kinds of frequencies are there at equal strength, understand? All kinds of frequencies is there, okay? So when you have 1, 0, 0, 0, when you do an FFT, you get a flat. Is that okay? Okay, all kinds of frequencies will be there, right? Now, when you input your FFT using 8 points, what is the period that FFT will take it? Is it 4 or is it 8? It's 8, understand? The length of the array is taken as the period of the signal, okay? So within one period, you have 2 impulses, right? Right? And this is the impulse train I'm talking about. Okay, this is the impulse train now. Train on impulses, understand? Okay? Okay? So it's train on impulses. Now, the interesting thing is when you have a train of impulses as your input, the FFT result also gives you a train of impulses, understand? Okay? So you have a train of impulses, FFT also gives you a train of impulses. Okay, never mind the 2, as I say, loudness doesn't matter, huh? Right? You always look at 0 or big numbers more matter, right? So for train of impulses, the FFT result is also a train of impulses, understand? Okay? Now, the other way is true, huh? Let's say in your time domain is a flat signal. In the time domain it's a flat signal, right? The reason we hear some noise is some sound is because of the vibration, right, in the air. Right? Right? And if it's a fixed signal, no vibration in the air, do you hear anything? No, right? Right? No, right? So when you have a constant number throughout, right? No vibration, constant number throughout, right? When you do FFT, you only get a non-zero number here, the rest of the frequencies are missing. Why there's a non-zero number here? The non-zero number is because the FFT, the very first number, gives you the so-called DC term, understand? Zero frequency. The first number represents a zero frequency, understand? So if your input doesn't have any vibration, right? doesn't have any vibration, the output will be, you have some non-vibration component here. Depending on the numbers there, you have big numbers there, you have a bigger number here, but the rest of the frequency are zero, understand? Okay? So when your input is a flat, the output only has got one number, the zero frequency component, understand? Right? So it's actually, you can see it's actually, they are going, just now when the input is an impulse, output is flat. Now when the input is flat, output is an impulse, right? Right? Okay. And for this case, it's the same. When your input 8 numbers of flat, right? Flat, no vibration at all, no variation at all. Output will have no vibration component, zero frequency. So that's all zero, right? Okay. And so far okay lah. Do you know what I'm talking? Okay. Now, there's another Fourier transform pair that you need to know, and that is the sine cosine. We do so much on sine cosine, right? When you do cosine, maybe I should just draw. Have a cosine wave. Cosine wave is like that, right? Cosine wave, right? And then you discretize it, right? Put all these values. You put all these values into all these all the values here, right? Put the values into this array here. And you do FFT. For cosine, what you get is you get two peaks only corresponding to the frequency, understand? If this cosine is 5 hertz, then this will be 5 hertz. Okay? And this will be minus 5 hertz. Okay? No question? You're bound to ask question. What is the question? What the hell is 5 hertz, minus 5 hertz, right? How can you negative? You can run 0 hertz, you don't vibrate at all. How can you do a negative vibration, right? Right? Again, a negative frequency is another mathematical construct. Okay? Because in our math there, there's nothing to constrain you from using the negative frequency, right? It never says that f has to be positive, right? Right? So you have a negative frequency component. When you do FFT, you have negative frequency component. Okay? Right? Don't think of physical meaning. There's nothing such as, you either vibrate or you are dead, right? There's no such thing as negative vibration, right? I don't know how to create negative vibration. Okay? Okay, so you have 5 hertz minus 5 hertz. This is cosine if you do Fourier transform, right? And then similarly, if you have sine, you do Fourier transform, what do you get? You go to your slide number. You go to slide number 36, right? You get something like that, right? You get something like that, right? In the cosine case, it is you get n over 2 here, right? Real numbers. Okay. In the sine case, you get minus j n over 2 plus j n over 2, understand? Okay? It's in your slide. Slide number 36. Okay? So for cosine, when you do FFT, you get 2 real number, understand? 2 real number peaks. For sine, you get 2 imaginary number peaks, understand? One is minus, one is positive. Okay? You have to know that cosine gives you real number, sine gives you imaginary number. Okay? We will do that, we need this, we need this when we do JPEG compression next time. Okay? Positive, both are real numbers. Cosine gives you real numbers. Need not be positive, but real numbers. Sine gives you negative numbers. Sine gives you imaginary numbers. Okay? And then in the slides itself, you will see that they repeat, right? Because it's periodic, understand? It's periodic, but think of it as one period. Always think of one period only. Just be aware that it repeats itself, but always think of one period, what happened within that period, understand? Because this is the result that you're going to get from FFT. Okay. So, impulse training. So, we look at a few important results for CPFT now. Impulse training. Impulse training in continuous time, right? In continuous time, this is also important. We talk a lot about discrete time axis, but sometimes conceptually you have to think of this continuous time axis also. Because that's how the real world signal is like, right? Real world signal is in continuous time, right? Now in the continuous time, you have a train of impulses also. You can have a train of impulses also. Okay? How to have a train of impulses? I keep on feeding you, right? Pum, pum, pum. Understand? Understand? Okay? Then you have a train of impulses. Okay? So this is a impulse train in continuous time. Again, this is a representation, right? This is a math representation. I don't think it's that complicated, but if you are having problem with all these things, don't worry. You just remember what I said. If you have 1, 0, 0, 0, Roll transform give you flat, right? If you have flat, they'll give you 1, 0, 0. If your input is a cosine wave, it gives you two peaks of real numbers. If your input is a sine wave, it gives you 2 peaks of imaginary number. One is positive, one is negative. Understand? Just remember these 4 things that I just said. Okay? Now in the impulse train domain, in the continuous time domain, you have train of impulses, right? And then in the train of impulses, if you do Fourier transform, you also gonna get back a train of impulses that we just seen that one. We just seen it just now, right? Now, there's another thing that you need to know. If I have this is called a rectangular function, right? This is called a rectangular function. If you do a Fourier transform, it is this thing, something called a sinc function, understand? Sinc is like sine of omega divided by omega, right? There are normalized version or whatever, but just remember this is a sinc function. Okay? So why do we need to know sinc function? Because sinc function describes what happens in reality, understand? Because in reality, am I able to give you infinite energy within a 0 time interval? Can I do that or not? Nobody can do that, right? If I can do that, I think you will fall flat directly. I lose my arm also, right? Right? You cannot do that. So in reality, what happened is I punch you very short time interval, but there's still an interval, understand? Not 0. Okay? So it's like a rectangular function, isn't it? It's like a rectangular function, right? I punch within a short interval and I hit. So it's like a short interval, right? It's a rectangular function. So you need to know this function because then the FFT is a sinc function. We need to know this concept because that's what happened in reality, understand? Okay? So that's if you put this rectangular function to be very, very high and very, very narrow, it is like an impulse, right? A realistic impulse. Okay? And the Fourier transform is a sinc function. Just remember, sinc function. The shape is like that. The shape is like that. And then there are normalized version of sinc function. I'm not too particularly worried about the exact math here. You just need to know that the shape is something like that. Understand? That's good enough for the class. Okay? Now, so another thing you need to know is Fourier transform properties is also important. It's also important. say do. Can you say do? Your name is Cleon. Cleon, you're the one who yeah, right? Cleon. And answer, right? Sorry? Answer. Cleon and answer, can you sing do? Can you sing Ray together? Right? Okay? So you do first, you do without you singing. Do. If I take this as Fourier transform, in the frequency domain, I got the frequency correspond to do, right? Right? Do, right? And then you sing, answer sing Ray. Ray, I got the frequency response, the frequency corresponds to Ray, right? You sing together do and Ray. Yeah. If I take this combined sound, what I'll see in the frequency domain is the do plus the Ray, understand? Okay? So this is known as what? Linearity. That's what the first equation says. Okay? Okay, linearity. That means you can give me a lot of sound. I just do one Fourier transform, right? I can know all the frequency components of your combined sound. You just add up together, understand? Okay? Now, there's another thing that is important is shift in one domain results in a phase shift in another domain. That means Cleon, you say do again. Do, right? I get the frequency corresponding to do, right? And then you say do. You say you wait for 2 seconds, then you say do. I record now. So in front is 0, right? That means his do actually came later, right? So it shifted, right? You still get the 2 frequency correspond to do, understand? It's just that now the phase is different, understand? The magnitude is the same, but the phase is different because it's complex number, right? So the vector rotates already now, understand? The magnitude is the same, understand? So that's what is meant by shift in one domain results in phase shift in the other domain. This is useful for pattern recognition, actually. Right? The other thing that's also important, which you will need to use this concept later when you do, say, JPEG compression, right? Cosine transform, kind of thing. If X is real, then X exhibits complex conjugate symmetry. Everyone know that this is called, everyone know what is a conjugate of a complex number, right? Complex number, conjugate of a complex number means this. If X is A plus JB, conjugate is A minus JB, understand? Okay? So this is and for this thing, if you take the absolute value, they are the same. Okay? So the complex number is, magnitude is the same as the magnitude of the conjugate, understand? Okay, so when X is real, the Fourier transform exhibits something called conjugate symmetry. Now, I want to bring you back to what I've been drawing here. Raining heavily now. Notice that every time I draw the spectrum, right? If I draw the spectrum, I always draw, see this is the frequency, right? I always draw like that. And this is 0, this is a positive frequency, this is negative frequency, right? Yeah, I always draw the 2 sides like symmetrical, right? Because I'm drawing the magnitude here. I'm drawing the mod of X here, understand? I'm drawing magnitude. The magnitude is always symmetrical, positive side, negative side, understand? Because it is complex conjugate symmetry. Okay? Okay? Now, what is important here is when this part is A plus JB, let's say this length here, right? This L, right? The L, the same length is away here. This will be minus JB, understand? Understand? One is A plus JB, the other side is A minus JB, okay? The magnitude is the same, but then, yeah, when they have complex conjugate symmetry, understand? Okay? Now this is very important, and this one only happens when the time domain signal is real, understand? Real numbers in time domain signal in the Fourier transform domain, you always get this kind of symmetry. That is why when I always draw symmetrical, understand? Is that okay? So, there are some proof here, I can leave it to you. The proof are actually quite simple to understand. Right, I leave it to you to go and read. Shift invariance shift property also, I leave it for you to read. Right? And why do we call shift invariant of magnitude? Right, because remember what I said. If close voice I initially silent and then he do, right? It's the same as do, right? But shifted version, right? In the frequency domain, the magnitude is the same. It's just that they get rotated. Understand? The phase is different. You understand what I meant by rotation, right? Or complex number rotation, because of the phase. Okay. Right, shift invariant property, this is just for info. Shift invariant property is actually useful for pattern recognition. Right? Let's say if I'm looking for the pattern in your voice, may the force be with you. Right? And I take a copy of the voice, may the force be with you. And then you give me another audio clip, and then that contains may the force be with you, right? Right? And zero elsewhere. Right? Right? So the shift invariant property is useful in the sense that if the signal that I collect starts from here, may the force be with you, right? And then zero. And then if your signal is at zero and then may the force be with you, I still can compare them because the magnitude of the Fourier transform for these two signals are the same. Understand? Okay? So with that, the next item is frequency resolution. Frequency resolution, I don't think we have much time to go very deep, but I just give some preview first. Frequency resolution answer, you see, just now in the time domain, right? In the time domain, every gap is a delta t, right? Let's say 1 millisecond interval, right? Yes? And you do Fourier transform in the frequency axis, right? You have the zero frequency and positive frequency, negative frequency, right? And I say, what the hell is negative frequency? It's just a mathematical construct, there's no physical meaning, okay? Okay, it's positive frequency, zero negative frequency, right? Okay? But if you ask me how many hertz do they represent? Is it 200 hertz or 400? I do not know because there's only a vector that's given to me with all these numbers, right, on the frequency axis, right? Now, in order to find out how many hertz, you need to know what is the resolution in the frequency axis. Understand? What's the gap? If this is 0.1 hertz, 0.2 hertz, etc., etc. And that's the frequency resolution that we want to do. I think next lecture we can't do it now. Right? That one will allow you to tell how many hertz. Understand? Okay? Now, I'm a bit worried because this class is exceedingly silent. Quiet. I'm not sure whether you understood or not. You know, you have to give me feedback, but how about this? Use the Canvas question, Q&A, to ask questions and then I'll answer them. Alright, and then if I find that you really need face-to-face coaching, I'll call you up to my office. Okay, and then I give you some face-to-face coaching, right? But as far as possible, try to use the Canvas to answer, because when you ask questions, everybody chip in. I love to see students helping to answer the question also, and by helping to answer the question, you also learn, understand? This one happened have to understand the concept, otherwise you find it more and more difficult. Alright? Alright, so use Canvas to discuss. I'll try my best to answer it as fast as I can. Right? And then if you really are lost, completely lost, you have to let me know. I'll call you up to my office and give you some tips. Alright? Thank you. And next week we have lesson, right? We have lesson and then we will move on to learning here. And the good thing about this year's Lunar New Year